Hello everyone. Welcome back to our mathematics classroom. Let me start with a simple question. Have you ever wondered how businesses decide what to produce and in what quantity when they have limited money or space? Imagine this, a furniture dealer has only 50,000 rupees to invest and storage for just 60 pieces. He sells tables and chairs. Each table costs 2,500 rupees and gives him a profit of 250 rupees. Each chair costs 500 rupees and gives him 75 rupees profit. Now, he wants to earn the maximum profit possible. So, how many tables and chairs should he buy? This type of problem, where we try to maximize or minimize a certain quantity such as profit or cost while obeying certain limits, is called an optimization problem. Such real-life problems appear in almost every business or production setup, and they form the foundation of what we call linear programming. So what exactly is linear programming? Let's break down the name itself. Linear means all our equations and inequalities involve variables raised only to the first power, no squares, no cubes. And programming here doesn't mean computer coding. It means planning or scheduling mathematically. So a linear programming problem, or LPP, involves finding the maximum or minimum value of a linear objective function like z equals 250x plus 75y, where x and y are our decision variables. But there are also restrictions or constraints, which are linear equations or inequalities, like 2500x plus 500y is less than or equal to 50,000. All the points that satisfy these inequalities together form what we call the feasible region, the area where all the conditions are true. Now, this idea actually builds on what we learned in class 11, linear inequalities. Remember how we used to draw lines like x plus y less than equal to 4 and shade the region that satisfied it? Here, we do something similar, but with an extra twist. We add an objective function that we either want to maximize or minimize. To find the answer, we plot all the inequalities, find the region where they overlap, that's a feasible region, and then look for the point that gives the highest or lowest value of the objective function. These corner points, where boundary lines meet, are especially important because the optimum value always occurs at one of these corner points. And that's the beauty of the graphical method. You can see where the best solution lies. Let's now identify the main components of a linear programming problem, or LPP for short. First, the decision variables. These are the unknowns we need to determine. For example, x equals number of tables, y equals number of chairs. Second, the objective function, which is the quantity we aim to optimize. For example, z equals 250x plus 75y. Here, z represents total profit. Third, the constraints, which are the limiting conditions such as money or space. Like 2500x plus 500y less than or equal to 50,000 and x plus y less than or equal to 60. Finally, the non-negativity restriction, which simply means x and y cannot be negative. You can't have negative chairs or tables. In short, every LPP can be summarized as maximize or minimize z equals c1x plus c2y subject to constraints a1x plus b1y less than or equal to k1 and x, y greater than or equal to 0. Linear programming isn't just a math topic, it's a powerful tool used across the real world. Industries use it to allocate limited resources, plan production schedules, and even minimize waste. Economists use it for cost minimization and profit analysis, while managers use it for transportation, diet planning, or workforce scheduling. Even computer scientists use similar optimization concepts in machine learning and operations research. So, Linear programming helps us make the best possible decision when there are multiple options and constraints. Let's bring all this together with the same furniture dealer example. We let X represent the number of tables and Y the number of chairs. Each table costs 2,500 rupees, each chair 500 rupees. The total investment limit is 50,000 rupees and the total items cannot exceed 60. So our constraints become 2500x plus 500y is less than or equal to 50,000 and x plus y is less than or equal to 60. Now, the profit he makes is given by Z equals 250x plus 75y. We plot these inequalities on a graph. The shaded region that satisfies both conditions is a feasible region. By checking the corner points, we find the combination of x and y that gives the maximum value of z. That's our optimum solution. So, let's quickly recap what we've learned today. Optimization means finding the best possible outcome within given limits. Linear programming is a mathematical way to do that when all the relationships are linear. It involves decision variables, an objective function, and linear constraints that define a feasible region. Using the graphical method, we can easily visualize and find where the optimum value lies, usually at one of the corner points. Linear programming is not just theory, it's used everywhere, from business planning to resource management. I hope you now understand how linear programming helps us plan efficiently and make the best decisions mathematically. In the next video, we'll explore how to mathematically formulate a linear programming problem from a word statement. See you there.